Hello again and welcome to another tutorial. I would like to show you how I created this resonance field or Chladni pattern and basically feeding the same graph that I created last time in the last tutorial with some scattered points and a bullet simulation, feeding this with another kind of field to drive the simulations. So let's have a look at the graph. It's quite straightforward and almost the same that we did earlier. So I have a rock generator here, and this time I calculated the radius and set the collision type to be sphere, and fed that into the set instance geometry node, then made a point grid, which looks like this, created the instance IDs, rotation and scale randomization, and then everything goes into our bullet simulator with the settings node and the rigid body instance node where we can set the parameters. Now there's a bullet field and the Chladni field. And this is what it looks like. Now when you invert the fields and play around with the frequencies, you can get all kinds of different interesting patterns out of it. Okay, so let's build this from scratch. Start with a new scene. Okay, let's start this with our trusty old rock generator. Maybe we can get away with less divisions this time. Here they are. And then compute on frame. So I only want to do this once. Set instance geometry and put this into the instance geometry input. Make a grid. And this grid can be flat. There we go. I have a node called generate instance ID, the same one that we created in the last tutorial. We're just creating one long value per point that we have in our grid and randomize it from 0 to 9 in this case. So we're getting all our different instances. Randomized rotation. Randomized scale. Yeah, something like this. And then we can create the bullet nodes. Simulate bullet, bullet settings, and the last one is source rigid body instances. Connect these. Now, since we haven't specified any collision shape yet, we are defaulting back to whatever the source rigid body instances node has in here. But what I would like to do is first of all use the point scale and then get the point positions on our rocks. And then compute the bounding sphere. because with the radius information, we can feed the primitive collision shape node from bullets. We set this to sphere, and in the sphere rollout, we can connect the radius. And then we'll set collision shape on our geometry and feed this in the graph. We have to start the bullet simulation on frame 1. Maybe reduce the steps again. Put some friction on a ground plane that we'll have to activate. And then we're good to go. Okay, so let's create a new compound. Call this Chladni fields. Dive in, and let's have a look at the math that we have to implement to get this going. So I found this formula, which is pretty easy to recreate, which will give us these patterns. And yeah, let's have a look at what we need. We need a position, x and y, but in our case that would be x and z. Then there are two frequencies, n and m, pi constant, and L is the length of the side of these Chladni plates. So let's go ahead and create some scalar fields. And the first one will be the constant n, or the frequency n that we want to input, and the frequency m, and a length. Then we'll need the scalar fields for the constant pi. And this is an internal mode as well, so make sure that you activate it. And then we'll need to get the position fields. And this will give us positions from whatever we are sampling in our graph. So if we have a probe geometry for our vector field or scalar field scopes, there's a geometry in there that will get sampled, and all these positions will be coming from these position fields. So since this is a vector field, we want to split this up. Vector 3 to scalar, so we can only take the x component and z component. Okay, what was that again? N times pi times x divided by L, and then the cosine of it. Let's do this. Multiply n times pi times x divided by the length. And take the cosine of it. And then we'll do the same for m and L. So we can just copy this and change the inputs. So we'll take m, pi, and z divided by the length, take the cosine of it, and then we'll have to multiply both. And the second half of the term is actually the same. It's just that m and n are reversed. And we subtract that. So subtract. And we'll take the whole calculation, we'll duplicate it. And now let's get n and m down here so we can switch them out. So n will go into this side and m will go into this side. We can subtract it and output the whole thing and have a look. Maybe create a field scope at this point, scalar field scope, and let's make a plane. Pipe this into the probe and make a terminal. And then the only thing left to do is input some numbers. So here in this chart we can see some examples. So we'll take m and n, some integer values, some low integer values, and an arbitrary length. So let's say 1, 5, and a length of 1. Now we have to increase the length. There we go, there's a pattern. And you can play around with these frequencies to get different looks. But the field is actually also outputting negative values that we cannot see the way this scope is set up. But we could just take the absolute So with the absolute value, we're also getting patterns where the Chladni field is negative. So yeah, to make these animations a little bit more interesting when using this field, I thought about inverting it and then blending between the two. So I'll just detach the instances for now. We can take the absolute value and invert it by creating another scalar field. Make it a value of 1, and then subtract the absolute value. Let's see what it does. Gives us the inverse. And then we could lerp these two. So the first is just the absolute value, second is the inverse, and the fraction is something that we might want to control. So make that a scalar field and get an input. Call this inverse. And then maybe we can edit the inverse to have a minimum of 0, a maximum of 1. So the slider doesn't go overboard. Now let's connect this. And see if it works. Yeah. Alright, so now we only have scalar fields, but what we need to inject velocities is get vectors going. So we'll take the output of OLED and take the scalar field and make a gradient field. And this will make a field, a vector field, that points from the lowest, from the lowest value towards the higher values. So let's get a vector scope. Same probe. We'll make another terminal. And here we can see that these vectors are pointing away from the 0 value towards 1. But one thing that I want to change is the magnitude of the vectors. We can see that in the areas where there is no weight, the vectors are quite small, and they're increasing when they're coming near our weight of 1. But it should actually be the other way around. So if I have some particles lying around here in this empty space, I want to attract them to the red lines. So the velocity needs to be high over here, and once they approach their final destination, the magnitude can be lower since I don't want them to overshoot, right? So they can settle in this area. And the way to do this is just normalize the vectors that we have. And this will keep the direction. And then we'll just take the inverse of this. So scalar field of 1, subtract. And then multiply this. Normals, inverse magnitude. And then we get what we want. We'll have longer vectors in this empty space, and then they get smaller and smaller until they approach the final destination here on the red line. Cool, so now maybe we want to remap this as well. So make an F-curve field. For the magnitude. Map magnitude. And the lengths of the vectors are fine. It's good to display them like this. And if we change the ramp, you'll see that you can influence it. And that's cool. But we also want to be able to accelerate the vectors, or increase the magnitude on these vectors. So maybe make another multiply. Add in a scalar field. I'll just copy this one. Pipe this into the input node. Call this magnitude. Oops. And let's get this to the output. Great, so now we have different patterns. We can change the length of the plate and get some interesting vectors going, inverse it, and change the way the field is interpolated. maybe we can make a switch node for both of our diagnostics. So make an if statement, and if it's enabled, we're going to output the scalar field. The same goes for the vector fields, like this. Make another input. That's to show the scalar. That's to show the vectors. And then we can switch it on or off as we like. Okay, that's our fields. Plug this into acceleration. Let's enable our solver again and have a look. Maybe we can increase the magnitude. Give us some more frames to play with. There we go. So now we can play around with this, inverse it. And make some interesting animations. So yeah, that's it. That's everything that we need to do to implement this. Have fun and show me what you've animated with this. Have a nice day.